Okay. Good evening, everyone. Good evening. Good evening, guys. Okay, so today's one shot is current electricity. Okay, so we have already finished electrostatics mostly. So today's topic will be current electricity, and in potential I did not cover capacitance, right? So capacitance we will cover it once we are done with current electricity. Okay, because it does not make sense to cover capacitance with potential. So we will study capacitance once we are finished with electricity and current. Okay, so today's lecture, guys, it will be mostly 2 hours, right? Yeah, it's going to be 2 hours only. So the class will go until 7:30 p.m. Okay, and we will try to finish as much as we can until 7:30. So we won't be able to cover much today, right? We won't be able to reach the, what do you say, the circuit questions today, but we will try to finish as much as possible. Okay. So, and yeah, so as you all know, this is mainly a board exam revision type of one shot. So we won't be taking too many JEE problems either. Okay. Hello, Shivanshu. Hi, guys. So we can start right away. Okay. So we will begin with the definition of electric current. Okay, then we will cover what is electric current density. And then, you guys have a lot of formulas regarding the drift velocity. That is very important for board exams and mains also. And then we move on to Ohm's law and its derivation. Okay. And the series parallel resistance combinations. Okay. So that is how the order of topics are going to be. Okay. So we will begin. So, okay, so electric current. So what exactly is electric current? So electric current is mainly a term we use to describe flow of charges, right? So in the first chapter, we were mainly dealing with charges at rest. Now we are going to deal with charges in motion. So whenever we have charges in motion, so let's just take a cross-sectional area. I'm looking at the side view of a cross-sectional area, okay? And this cross-sectional area, I'm calling it as S. And on the left side of this cross section, I am taking a bunch of charges, okay, which I am considering it as points only. So you can give these charges different names, okay, Q1, Q2, Q3, etc. So, but these are all charges, okay. Now, if I say that these charges are in motion, like all these charges have some velocity, and they are about to cut this cross section S perpendicularly. So we can say that these charges are going to cut through this cross section S, right? So if you have a constant flow of charge through any cross sectional area S, then we say that there is a current through that cross section, okay? There is electric current through S, okay? Where S is any cross-sectional area. Okay, so I'm looking at the side view of this. In case there are charges flowing through S every second, we can say there is electric current passing through the cross-sectional area S. Now, in our study, we will mainly deal with current carrying wires, right? So if this is like a cylindrical wire, and it's given that it is carrying a current I, then what that means is if you imagine any cross-sectional area inside this, like this, every second some charge is going to cut through this cross-sectional area, okay? So you can imagine charges flowing inside the conductor like river flowing in a tube, okay? So that is how we are going to imagine electric current. It's the flow of charge similar to how a river flows inside a cylindrical tube, okay? So now we can get into the mathematical definition. So whenever there is a transfer from one side of the area to another side, okay, consider any area. Whenever there is a transfer of charge from one side to another side, we say that there is some electric current through the area. And this is a certain convention that we follow. That is, if we have a positive charge, if the moving charge, right, current basically means moving charges, right? But if the moving charge is a positive charge, like in this case, then if the positive charge moves to the right, we denote the direction of current in the same direction as well. Okay, so if positive charges move to the right, current is also in the right. But for negative charges, the rule is opposite. If we have a negative charge, a negatively charged particle, and if these particles are moving to the right, then the current is taken to be in the left direction. So basically, in our usual conductor, and if we connect it across the ends of a battery, we know that there will be a current in this circuit, right? And the direction of current is from the positive terminal of the battery to the negative terminal, right? So this is the direction of current, right? This is the direction of current, which means now in the conducting wire, as you all know, it's the electrons that are moving, right? In a conductor, it's the negatively charged electrons that are moving. Electrons are the moving charges, right? The positive charges are in the nucleus, okay, and the nucleus you can consider they are kind of rigidly fixed, okay. So electrons are very much more lighter and much more smaller, so they can easily move through the wire, okay. Nucleuses of these atoms are kind of fixed. So inside the conducting wire we have electrons moving, and if the direction of current is in the anti-clockwise direction, like this, then that means the electrons are moving in the opposite direction, right? This electron is moving in this direction. So these electrons must be moving in the direction opposite to the direction of current, okay, because it is a negatively charged particle. So that is something to keep in mind. So if we have a negative particle, the direction of motion, if it is to the right, current is taken to the left, basically opposite to the direction of motion of the charge, okay. And if it is a positive charge carrier, then current is in the direction of velocity. So that is something, that's the first thing about electric current, and this is the convention. This is how it is defined. Next is we are going to define the mathematical relation of current. So first we will talk about average current. So we will take the cross-sectional area once again, okay, and imagine that there is current flowing in the right direction, okay. So positive charges cutting through this cross section every second. So if we observe for delta t time, okay, delta t time, okay. So using a stopwatch, if we observe for delta t time, let's say a charge of delta q cuts through this cross sectional area S, okay. So in this time delta t, if the charge crossing the area is delta q, then we define the average current for this, okay. The average current through this cross section is delta q divided by delta t, okay. So the more charge that passes through S in this time, the greater the current, okay. So this you can also read it as the rate of flow of charge, right? The rate at which charge crosses this area. So if charges are moving much more rapidly through area S, then delta Q will be greater, right? More charge will pass through S in a given time, so more will be the current. Now, what do we mean by instantaneous current? So current at time t, by this we mean instantaneous current, right? Current at an instant. So this is similar to how we went from average speed to instantaneous speed in class 11th, right? So for instantaneous speed, all we have to do is observe for a very short time duration. Here we observed for a finite, like a slightly large time duration delta t. But if I want the current at any instant of time, all I have to do is observe for dt time. Okay, observe for dt time. Dt means a very small time interval. I mean, if we go by the definition, exact definition, it's infinitesimally small time interval. It's as small as you can imagine. Okay, so in this time, of course, the charge that cuts through S will be a very small charge, right? So that I'm saying is a small charge of dq. Small charge of dq passes through S. Then the instantaneous current, which means the current exactly at this instant, this we can say is dq by dt. This we can say is dq by dt. Okay, so now if you know how charge changes with time, you can simply differentiate the charge to get the current. Okay, so to take a simple example, I think I have, I'll just make one example. So let's say we have a cross-sectional area S, okay, and we know how much charge crosses this S as a function of time. Okay, so let's take a simple example. Q naught 1 plus kt. Okay, so actually not Q naught 1 plus kt, I'll take Q naught t square. Okay, so this is how charge, the amount of charge crossing S varies with time. Okay, so as time increases, more and more charges pass through S. The question is, if this is how charge crossing varies, what is the current? What is the current at any instant of time? Okay, so this is a simple differentiation. You'll just have to differentiate Q with respect to time. Okay, so Q naught is a constant, so we won't mess with that. Derivative of t square, guys, you should remember some simple derivatives. It will be 2t. Okay, so current as a function of time will be 2q naught t. So if you put different times in this equation, you will get the current at different times. Okay, so if you put 3 seconds here, you will get the current at 3-second time, and so on. Okay, okay, great. So now there is also the reverse process where you could be given the current. Okay, the current will be given to you and they will ask you what is the charge that crosses the cross section after, let's say, 5 seconds. Okay, this can also be asked. So this is the reverse question. So in the previous question, the charge varying with time was given, right? Q as a function of t was given and we found out current. So in this case, if current is given as a function of time, how to find the charge? So this is simple. This is just the reverse process, right? So current, write it as dq by dt and just separate this. dq, write it as current into dt. Okay, and now the thing is we will integrate on both sides. Okay, and we will integrate until what time we need the charge. So let's say we need the charge flow from 0 to delta t, and in that time I'm saying the charge flown is q. So left hand side will become q, right hand side will become, that will depend on I, but the general formula is it's going to be integration of I dt from 0 to delta t. Okay, this will be the charge that flows in a time delta t. Okay, now this also, if you guys have studied integration, when you have integration of I dt from some time 0 to delta t, this is also the area under the IT graph. The current versus time graph from 0 to delta T. From 0 to delta T. Okay, so here the thing is, in the diagram given, they are integrating the current from T1 to T2. So this will give me how much charge flowed through S from T1 to T2, and that will be the area under the current versus time graph between T1 and T2, which is going to be this area. Okay, so the area under current time gives me the charge flow. Okay, great. Now on this we can do a question. So try this question, guys. Try this question out. So if it is not visible, the current is given. The current is given as 2 plus 3t. So how current changes with time is given to you. You have to calculate the charge that crosses through a cross section of the wire in 10 seconds. Okay. So you have to find the charge flown in 10-second time. Okay, so give it a try for 1 minute. Priyanshu, the PPT will be available right after the lecture. Okay, it will be in the description only. Okay, I think it will be in the comment section. You will get it. Don't worry. So any answers, guys? Okay, so here we will have to go through integration, right? So current is given. So how do we find the charge flown? Charge flown will be integration of IDT. So you will have to do some integration here. So instead of I, we will put 2 plus 3t. Okay, now we will integrate this, right? So in the integral, you will have to, so the time we need the charge until 10 seconds. So time we will put it from 0 to 10 seconds. Okay, so now 2 dt, so that will be 2t once you integrate it, and you will have to put the limits. Lower limit is 0, upper limit is 10. And if you integrate 3t, so the 3 you can take it outside, and the integration of t will be t square by 2. Okay, and once again the limits will be from 0 to 10 seconds. Okay, now you can put the upper limit, so that will make it 20. This term, it will be 20, 2 into 10, and this term will be 300 by 2, 150, right? 150. So that is going to be 170. Unit of charge is coulomb. Okay, unit of charge will be coulomb. Okay, so the answer will be option B. The answer will be option B. So that's it. That's all. Yes, it will be 170. Okay. So I mean, other than that, you know, the SI unit of electric charge, I guess all of you know, like the SI unit is coulombs, right? This we already covered in the electrostatics chapter. And the SI unit of current is actually, I think I've written it over here. Okay, the SI unit of current is ampere. Okay, AMPERE, and 1 ampere. So use the relation I equal to Q by T. So you can get the definition of 1 ampere. So 1 ampere is SI unit of charge is 1 coulomb, SI unit of time is 1 second. So 1 coulomb per second is defined as 1 ampere. Okay, and ampere or current is one of the fundamental physical quantities, right? Current was one of the fundamental physical quantities, if you remember, the 7 base physical quantities. So the dimension of current will be simply ampere raised to power 1. Ampere raised to power 1. Okay, and if you want the dimension of charge, what we will do is we will use the same relation, I equal to Q by T. So dimension of charge will be dimension of current into dimension of time. So that will be ampere into time, AT. Okay, so that's the dimension. Then yeah, so this is also important. Okay, this is an important note to keep in mind. The electric current physical quantity, it has a direction and a magnitude, but it is not a vector quantity. Okay, so it does not follow triangle law of vector addition basically. So even though like a current does have a direction, right? Electric current like does have a direction. It can either flow to the right or to the left, but it is not treated as a vector quantity. Okay, there is a different physical quantity called as the electric current density, which we will discuss, or current density, right? That is treated as a vector. Okay, so electric current is a scalar only. Okay, so electric current is a scalar quantity only. So you will never see it represented as a vector. Okay, so to represent a scalar, you only need the magnitude, like 10 amperes, etc., 10 milliamperes. You will never see a current represented as a vector quantity. Okay, yes, it will be 170. Great. Okay, then so now we can discuss about electric current density. Okay, so current density. So current density, for that first we will have to imagine a space in which there is a flow of current. Okay, so I am taking this cylindrical region and some current is flowing to the right like this. Okay, some current is flowing in the right direction. Electric current density, when we talk about it, we always talk about it at a point, close to a point. Okay, so I am choosing this point. Near this point, we will have to take a very small area of cross section. Okay, a very small area of cross section like this. Okay, so for explaining this, I am choosing a big cross section. Now, if current is flowing throughout this area, through this cross sectional area S. Okay, through this cross sectional area S, there will be some current that goes through it, right? Like this. Let's say that current is I. Let's say that current is I. Then the current density, we use the symbol J for that. Okay, it is defined as the current I divided by the area of cross section S. Okay, now as I said earlier, we define current density at a point. Okay, at a point. So we choose an area of cross section that is very small. So it's not I and S, it should be di and ds. Okay, so this I will write it as the average current density. So actual current density will be di by ds. Okay, di by ds, because the area of cross section, if we want the current density at this point P, we will have to choose a very small area of cross section like this, ds, and if the current cutting through it is di, then we define the current density as di by ds, okay, current per unit area through it. So it tells us about how much is the density of current cutting through any area, right? So if I am talking about a small ds area, if more current passes through it, greater is the current density through that ds, okay? So, so the unit also you guys can just see, it is going to be current divided by area, right? So ampere per meter square, okay? And the most important thing is this is a vector quantity, okay? The current density J, this is a vector quantity. It is defined for a point, defined near a point, and direction. So whenever we talk about a vector, we have to tell what is its direction. So direction is along the current, okay, along the current direction at P, at the point P, okay. Now, so that is all about current density. There is some extra stuff as well. So we'll start with that. Okay, so now the next thing is J equal to di by ds, right? So di, I can write it as J into ds. So this is also an important relation. So if this is that cross sectional area, okay, that we were talking about, if I want the current through a very small ds area, if I want the current through a very small ds area, let's say current is coming out of the page. Current is coming out of the page. Okay, so for those who don't know this symbol, this circle and a dot. So circle and a dot, this is used to represent out of the page, okay, out of the page direction. And this will be very useful or not useful, very important in magnetism. And a circle and a cross means into the page, okay. This means into the page. Okay, so when I say the current is in the dot direction, that means you can imagine charges are coming out of the page, okay, and this is the cross sectional area. The total current is I, and let's say this radius is small r. So if I want the current coming through this small area ds, all I have to do is use this relation, di equal to j into ds. Okay, so here how do we find j? J is going to be current per unit area, right? So the total current is I, and it is distributed in pi r square area. So j divided j, I can write it as its magnitude, I can write it as the total current divided by the area in which it is distributed. Now if I put it back here, I'll get the current through ds area. It will be current per unit area multiplied by the small area ds. So this is also important. This way you can get the current just through the small area ds, just through the small patch ds. So it's actually just the unitary method. If the total current is I, and if it is distributed in pi r square area, then I by pi r square is the current per unit area. Current per unit area multiply with the area ds. This will give me the current through ds. Current through ds area. Okay, so I'll think I have a question on this topic. Yeah, so like in this question, okay, so I'll modify this. Okay, so this is a rectangle and I'm trying to draw a cuboid here. Okay, so this is the length of the cuboid. And something like this. Okay, almost good. So if I tell you that this is the length of the cuboid, okay, and these two side lengths I am considering it as B and H. Now, so I'm connecting some battery between this point and this side, okay. So if I'm connecting the battery between this side and this side, current will be flowing along this L length, okay. So from the side view, I will see this L length. From the side view, I will see only this L length and this length, which is H, right? And current I am giving you, it is flowing in this direction, parallel to this L line, okay? So current is flowing like this. Current is flowing this way, parallel to L. So in this case, what will be the current density? In this case, what will be the magnitude of current density? So try this out, guys. Try this out. What will be the magnitude of current density? So that is the question. Here, what is the magnitude of current density? Current's magnitude, you can take it as I. Okay, the current flowing through this conductor, you can take it as I. Try this out, guys. Any answers? So in the last question, we considered a circular cross section, right? And in this case, when we had current flowing like this, then how did we find the current density? It was the current I divided by the area, the perpendicular area through which the current cuts, which is this pi r square. area, right? This was the current density in the previous case. So here what will be the answer? Here the thing is, you will have to check what is the area through which current is cutting perpendicularly. Okay. So current is going parallel to this L side length, right? So what is the area perpendicular to this L length? Okay. So that is going to be the area that we want. Okay. So we want this area. Wait. We would need this particular area. Okay, and in this view, what is that area? It's going to be this area, right? So that is going to be a rectangle whose area is B into H. So this area, this red area is simply B into H, breadth into height, right? So J here will be the current I divided by the perpendicular area which it cuts, which is BH. Okay, which will be BH. I divided by BH. That will be the answer. Okay. Great. Now, so that was about current density. Now there can be a different question that can be asked from here. They can give you current density. Okay, current per unit area they can give. Let's say it is equal to 10 raised to 6. Unit is amperes per meter square. Okay, this means in 1 meter square area, we have 10 raised to 6 ampere current. Okay. Then we can have a cylindrical wire. We can have a cylindrical wire given. Okay, and current is flowing through this wire. And then the question can be, what is the current through? What is the current through? Let's make it a like a cylindrical wire with a hole, something like this. Okay. So current is flowing through this parts only. Okay. Current is coming out through these sections only. There is no current in the middle part. Okay. So you can think of this like a wire with a hole in the middle. Okay. So if I draw the side view, it will look like this. The outer circle, and this is how the hole will look like. And current, let's say it is coming out like this perpendicularly. There is no current in the middle hole. Okay. Then the question can be, what is the current through this wire? What is the current through this wire? Okay, and this inner radius, let's take it as R1. Outer radius, let's take it as R2. So how do we solve this? Here the thing is, I know the current through a unit area, right? I know current per unit area. So if I want the current in this area, right? I want the current in this area. I'll just have to find out this area, whatever that is, and multiply it with J. So if I want the current, all I have to do is do J multiplied with A, right? J into A. So what is the area of this part? This part that I shaded. The area of the total circle is pi R2 square, right? Area of the total circle is pi R2 square. Just subtract the hole's area from that. So that will be minus pi R1 square. So this is going to be pi into R2 square minus R1 square, right? This will be the area. So we need the current through this area. So that will be current per unit area into this area. Okay, and now you can substitute J as well if you want the answer. Okay, so this type of a problem can also be asked. Then that is all for current density. Now we can move on to the next variation of this. Which is when the area is not perpendicular to the current, right? So in the previous cases, what we discussed was when current was cutting the area perpendicularly, right? In these cases, we were able to write di as J into ds, right? Now, what if the current does not cut the area perpendicularly? That is what we are going to see next, okay? Then there is a slight modification. So I'm saying current is flowing parallel to this tube, okay? Current is flowing parallel to this tube. And instead of taking my ds area like this, okay, I'm choosing it like this. I'm choosing my area like this. The current is still flowing in the right direction itself, okay? But my area is like this. It is bent at an angle. So this area vector, I am calling it as some ds. Okay, it's a very small area only. And yeah, so it's ds. Now, whenever you are given an area, ds, okay, then the direction of the area vector is important. Area vector is always perpendicular to the area, okay. The area vector, similar to in Gauss law, how we defined, we will define it perpendicular to the area, okay. So this will be ds vector, okay. Its magnitude will be magnitude of the area, right. Now, what is the direction of J? J's direction is the direction of current, which will be to the right, okay. Current density's direction will be J to the right. Current density will be J to the right. In this case, we want to write a relation similar to this, okay? Relation between current and current density. So let's take this angle as something theta, okay? So if this normal is making theta with the x-axis, then the area will make theta with the y-axis. This angle will also be theta. And which means this angle will also be theta. This angle. Okay, so here the thing is, the main thing you have to remember is, here you will have to choose the area, the component of the area perpendicular to the current, okay, similar to this case. Okay, so this area, this purple area, we can break it into two different areas. This purple area, we can break it into two separate areas. Area 1, area 2, okay, two separate components. And if this is ds and this angle is theta, then this area perpendicular to the current is ds cos theta, and this area parallel to the current is ds sin theta. Okay, parallel to the current, it is ds sin theta. So now what is the original relation? Original relation was, if current cuts area perpendicularly, then I can write di as J into ds. So I know that my current will cut this ds cos theta perpendicularly, right? So in this case, when we have an area at an angle to the current, I can write the current as J into ds cos theta. okay, which I can also write it as ds perpendicular. Area that is perpendicular to current. Okay, area that is perpendicular to current. Now J into ds into cos theta, if you remember Gauss law, this is similar to the electric flux expression, right? So this will become J dot ds. It's simply a dot product. J dot ds. Okay, so in this case, how do we get the current? If J and ds is making an angle theta with each other, then the way we get the current is by taking the dot product. In this case, in the simple case, area vector was also in the right direction and current is also in the right direction. So in this case, theta was 0, right? So it will be J into ds into cos 0, which will be J ds. Okay, and what happens if the area is like this, parallel to the current? That is easy to visualize, right? If the area is parallel to the current, then of course no charge will cut through the area, right? For current to exist, some charge should cut the cross-sectional area. So if area is parallel to the current like this, then here the current will of course be 0. Here the current through this area will be 0, okay? And using the formula also you can see, it will be J ds cos 90. So it will be 0 only, okay? All right. So this relation also is important. This relation is also important. Okay. So now we can talk about so we can start getting into the drift velocity discussion. But before that, we will talk about conductors for a bit, right? So I'm choosing a conducting cylinder, okay? So conducting material in electrostatics, we discussed this. So when we have a conductor, it has a sea of free electrons, right? It has a sea of free electrons. So what does that mean? That means the electrons present within the conductor are free to move. They're not bound or fixed anywhere. So to take a simple example, let's say I bring a very positive charge to the left side. So the thing is, it won't affect the plus charges that much, but because there is a bunch of free electrons in the conductor, the positive charge will attract those electrons and they will come to the left side. Okay, so there will be a large negative charge density on the left side of the conductor near this positive charge. Okay. Now, similarly, if you take this positive charge and bring it to the right side, now these electrons will run to the right side. So this means this simply means that the electrons have freedom to move inside the conductor. Okay. So now the thing is, we are going to discuss how we will generate a current using a conductor. So when there is like no electric field present in the situation, we need to understand how an electron kind of moves inside the conductor. Okay, so I'll just zoom this thing. So if this is the conducting materials insides, okay, if you simply track an electron, okay, if you simply track one of these free electrons, they kind of move like how gases or gas particles moved in thermodynamics, if you remember. If you guys remember the theory from KTG, the gas particles, they were moving very randomly. So the electrons also kind of move like that. if there is no electric field present. They move from one location to other, then let's say some collision happened here, and then it was moving in this direction, and then some collision happened here, then it will move in this direction, let's say, and then it moved in this direction, and some random motions will happen to the electron. So a random electron, if you track it, its motion will be random. Its motion will be random. Okay, and I mentioned some collisions happening, right? So collisions, you can think of this like, so if this is a copper conductor, there will be large copper nuclei present everywhere, right? So these copper nuclei are like huge spheres compared to the electron. So they will collide with these copper nuclei present everywhere. And these collisions will deflect the electrons in different directions. So after the first collision, electron moved like this, and after the second collision, electron moved like this, and so on, right? So it's a very random motion of the electron in a zigzag path, okay? Now, this is an important part, okay? But yeah, so the important idea is electrons are still moving, right? Even when the external electric field is 0, the electrons are still in motion, okay? The electrons are still in motion, random motion, okay? But even though the electrons are in motion, in this case, the current will be 0, okay? In this case, the current is going to be 0. So let's see why is the current 0 in this case. So the idea regarding that is, if you take a cross-sectional area, so for current, you always need a cross-sectional area, right? So if we take a cross-sectional area, somewhere like this, for current, I need to find out what is the total charge crossing this cross-sectional area in a given time dt or given time t. So that, if you notice, so there is not just one electron present here, right? I just drew the diagram for one electron, but there are millions and millions of electrons here, right? So you can imagine that there are, so I'm just taking a simple example. Let's say at any given instant, there are 100 electrons moving to the right, and let's say there are 100 electrons moving to the left, because it is very random, right? So because the electrons are moving very randomly, at any instant, if n electrons are moving to the right, then n electrons will also move to the left, okay? And hence, as a result, the net charge crossing this cross section will be 0. So even though the electrons are moving, in this case, the electrons' random motion does not contribute any current, okay? So electrons random motion does not contribute to a current, okay? And this is of course expected also, because if the random motion contributed a current, we will get a current in a conductor without any battery, right? But we know that if we don't connect a battery, then we don't get a current. Okay, so now then how do we create a current now, right? So the answer to that is, we will apply an electric field, okay? we will apply an electric field. And what does an electric field do? An electric field will apply an electric force on the electrons, right? Or like in this diagram, we're assuming the positive charges are moving. So the electric field will apply a force on the positive charges, right? So if I choose a positive plus Q charge somewhere, and if I place it in an electric field, remember from the electrostatics chapter, the force on the charge will be given by QE, right? Now this force will move the charges, right? This force will move the charges. And here we will talk about a concept known as drift velocity. Okay, drift velocity. Now this is an important idea to understand. Drift velocity, first of all, is not the total velocity of the charge. Okay, like here I talked about electrons random motion, right? So the electron will have some velocity, right? This is the random velocity of the electron. It is in some random arbitrary direction. But when we apply an electric field, because of the random motion of the electron at the start, the electron will move randomly like this, like this, like this. And because of the random motion, the electron does not move anywhere. Okay, like it does not displace to the right by that much. But when we apply an electric field, so because this is an electron, let's say I'm applying an electric field. Let's say I'm applying an electric field to the left. So on the electron, the force will be acting to the right, opposite to the electric field, right? So in the previous case, the motion was random. The electron was not getting any motion, any net motion. Right now, what will happen is it will still be a zigzag path. Okay, it will still be a zigzag random path. But the electron, because of the electric force, it would have moved forward by some distance. Okay, and that is defined as the drift. So in the previous case, the motion was very random. The motion was very random. But the electron wasn't moving anywhere. Okay, it will go here, there, and there, and it will come back to the original position. But now the thing is, the electron will still have the random motion, right? That random motion will not go anywhere. But because of this electric force to the right, it will slightly drift to the right. So that drift per second is what we call as the drift velocity. Okay, and it's the drift velocity that gives us the current. Very important thing to notice here is that, I think I wrote it here, yes. When we apply the electric field, the electrons on an average begin to advance by a velocity of the order of few millimeter per second to few centimeter per second. So this drift speed is not very high. It is a very small speed. Okay, its order is centimeter per second or millimeter per second. It's a very, very slow speed. Okay, but it's this drift velocity of the electrons, this extra drift speed of the electrons, that generates the current. This results in the current in the conductor. Okay, so now the thing is, there is a formula that we have to derive about the drift speed and the current I. So in this example, I'm choosing a slightly different case where we have a positive charge drifting with a speed Vd, a very slow speed Vd to the right. So if the positive charges are moving to the right, that means the current is along the right, conventional current, right? So now we need to derive an expression of the current I and this drift speed. Okay. So that is what we are going to be doing. So for that, what we'll do is, so in the first page I discussed this. Take any cross section, right? How do we find the current through this cross section? We observe for a time dt and see how much charge dq cuts through this, right? Then dq by dt will give you the current. So here, let's say I am choosing this cylinder. Okay, so here, as you can see, there is a cylindrical cross section here. So I just have to see how much charge crosses this cylinder in the next dt seconds. So the drift speed of the charges is Vd, right? Drift speed of the charges is Vd. And if that speed is Vd, what is the distance traveled in dt seconds? It will be speed into time. It will be speed into time, right? So in the next dt seconds, the cross-sectional area will move forward by v into t, speed into time. So we just have to find out how much charge is there in this small cylinder. Let's call the small cylinder's charge as dq. Okay, so our element is this small cylindrical element. This width is very small. It is equal to the drift speed into dt, speed into time, and it will have some plus charges inside. Like this. And this area of cross section, I am taking it as A. So I just have to find how much dq charge is there in this cylinder, in this cylindrical disc, and divide it with dt. That will give me the total current, the current in this circuit. Okay. Now, how do we write dq? This is important. Okay. So for writing dq, first of all, this is a volume, right? This is a cylindrical volume. Its length is v dt, area is A. This is a cylindrical volume. So I need the total positive charge present in this volume. So what I define a certain quantity, which I use the symbol n, and n is the number of free charges. Free charges means the ones who can move, right? Current is contributed only by those charges who can move. So number of free charges per unit volume in 1 unit volume. So in a unit volume, what is the total number of charges that can move? That is going to be n. Then we multiply this with the volume, this particular cylindrical volume. This will give me the charge present in this cylindrical volume. Okay, so what is the volume of a cylinder? This will give me the number of charge, not the magnitude of charge. So what is the volume of the cylinder? Length into area, right? So A into Vd into dt. So this thing that I multiplied is the small volume of the cylinder. Okay. So if n is the number of charge in unit volume, and if I multiply it with dV, what do I get? I get the number of charges in dV volume, right? Number of charges in dV volume. But I don't want the number of charges, I want the magnitude of charge inside. Okay. So for that, what I'll do is I'll just say, in this case where we have the positive charge, the charge of one positive ion is Q, or one positive charge is Q. So I'll just multiply with Q here. So this is the total number of charges, multiply with the magnitude of one charge. That will give me the total magnitude of charge. So NAVD into Q into dt, this will be dq. So what is dq again? N AV dt, Vd into t, sorry, Vd into dt. and finally multiplied with Q. Okay, so now for the current, all I have to do is divide with dt on both sides. Right, so this term just goes away and we get N into area of cross section into Vd into the charge Q. This will be the current through the conductor. Okay, but here the thing is, we took a random case where we had a positive charge moving with a charge Q, right? So when we are talking about conductors, which are the charges that are moving? Electrons, right? So Q will be equal to E. Magnitude of the charge will be equal to E, charge of one electron. Okay. So the formula will become NEA Vd. So this is the important relation between drift speed of electrons and the current I. So we applied an electric field that gave the electrons a drift speed, and because of the drift speed we get a current. Okay, so we can also define the current density here. Current density's magnitude will be current divided by area, so that will be NEVD. NEVD. So this is the current density relation and current relation. Okay, so the only thing to remember here is, for the conductor case, if the electrons are moving to the right, okay, so E minus means electrons, okay. If the free electrons are moving to the right, then that means the current is to the left. Then that means current or current density, they're both to the left, even though the drift speed is to the right. Okay, for the conductor case, if electrons are moving to the right, current will be to the left. Okay. So this is the question related to that formula itself. Now the first thing is number density of free electrons in copper. So this is basically our N, which we discussed, right? The number of free charges in a unit volume. For a conductor, we will talk about conductor, who is the free charge. For the conductor, the free charge is electron, right? So we will say number of electrons in a unit volume, and it's also known as the number density of electrons. Okay, like in this question, it is mentioned number density of free electrons. That means the same thing. Okay, so there are nearly 8 into 10 power 28 electrons in a unit volume in copper. Then copper wire's area is given, current is given. So this, you guys can try this as homework, okay, but it's simply application of that formula, right? I equals NEA Vd. So everything is given basically. I is given, N is given, E is known, area of cross section is also given, but you have to find the drift speed. Okay, you have to find the drift speed. So it's a very easy question. So it's a JEE Mains problem, and these questions, these types of problems can appear in board exams also. Okay, so so this, you can try this as homework after the lecture. What else? Okay, so now there is another relation. Okay, so this first part of the chapter is full of formulas. The drift velocity part. So So this relation is also available in your NCRT if you check it. The relation with drift speed and electric field intensity, electric field magnitude. So we saw how current and drift speed is related, right? There is also a relation between this drift speed and the electric field. Okay, now the derivation for this, it is a slightly lengthy derivation. So I'll just mention the result here. So if we are once again talking about the conductor situation, okay, the conductor situation where the electron is drifting with the drift speed, okay. So if electron is drifting to the right, then the electric force was applied to the left. Sorry, electric field was applied to the left. So in the conductor's case, the drift speed and electric field are related as E by m into tau, okay. Its magnitude is related like this. So, I'll explain each term. So here E is the magnitude of the charge of electron, m is the mass of the electron, okay. E is the electric field, of course, and this tau is known as the time between average time. It depends on the material, by the way. So average time between any two successive collisions, okay. I'll explain what that means. So, as we discussed that the electron is not moving freely inside the conductor. It will always collide with the big positive ions, right? There will be a massive, let's say if it is a copper conductor, there will be the copper nucleus or the copper positive ion somewhere here. And if the electron is moving like this, it cannot freely cut through the copper, right? There will be a collision happening here. Then it will start to move in this direction. Okay, and then once again it will drift, and once again it will collide, right? And once again it will drift. Motion will be something like this. This electron's motion is filled with collisions again and again, okay? It will keep on colliding with the copper ions. There can be impurities in the conductor as well. So the average time between any two successive collisions, okay, which means if there are, let's say, two big ions in the path of this electron, okay, so the electron is moving this way, and here a collision happened, collision number 1, and then it went and hit the other atom like this, and here collision number 2 happened, and then the electron was moving like this. So the time between these two collisions, we define it as delta t, let's say delta t1, 2. This is the time between collision 1 and 2. So tau, what is tau? Tau is the average of these times, okay. So usually this depends on a lot of things, okay. It depends on the material, it depends on the temperature and stuff, but it's usually like 10 raised to minus 9 seconds, which is like a nanosecond or something, okay, depending on the material and temperature. So what this means is an electron collides with another positive ion every nanosecond. So every nanosecond the electron bumps into another positive ion. So that is your tau. It's also known as the relaxation time. It is also known as the relaxation time. So these things are just important to keep in mind, okay. So never keep the understanding that the electron is free flowing inside. The electron always bumps into these guys, okay. The electron always bumps and there are collisions inside. But when you apply an electric field, the electron gains a slow drift velocity to the right. So it will start to slowly drift to the right, even though its actual motion will look something like this, right, a zigzag path. But on average, when we look at the electrons, they will slowly drift to the right. Okay, so this formula is also important, guys. The relation between drift speed and the electric field. So Vd is E tau by m. Okay, so the derivation for this, I'm not going through it right now because this is actually a slightly hard derivation. So it will take approximately 20 minutes to derive this. So the thing about this derivation is a lot of people actually give the wrong derivation. Okay, so I don't want to give the wrong derivation here. So I'm skipping this for now. Okay, then now we can talk about Ohm's law. Okay, the J equal to sigma E relation. We'll first talk about that. So what are the relations we learned? We discussed the relation between J and Vd, right? It was NeVd. This was the relation between J and Vd. And we also discussed the relation between Vd and electric field. Okay, so we have these two relations, and I'm taking the original case itself where we apply an electric field, and electrons start to drift to the left, which basically means current is to the right. So first I'm trying to get a relation between J and electric field E. So I'll try to get rid of this Vd. So J, I can write it as Ne, and instead of Vd I will substitute this. Okay, so this is actually Ne square tau divided by m. So this is a constant factor multiplied with the electric field. Okay, so it turns out that the current density is actually proportional to the electric field if we keep the other things constant. So these are all constants, right? Tau depends on temperature, by the way. Tau depends on temperature. So we'll discuss about this. But if I keep the temperature fixed, the material fixed, we can say J is proportional to E. So this is known as microscopic Ohm's law. Microscopic because if you choose any point inside the conductor, there if the current density is J, then the electric field will be in the direction of J. Okay, electric field will be in the direction of J, and their relation is given by this formula. Okay, I'm not rewriting, it is given by this formula. So if you increase the electric field, you increase the current density. Now this constant over here, this is given another name called as the conductivity sigma. Okay, conductivity. Okay, and so if you get rid of that whole formula, then you can write J as sigma I. Okay, and you can also write it as a vector relation. J and E actually have the same direction. Okay, all right. So this is also one form of Ohm's law itself. So this Ne square tau by m, this formula is also relevant, guys. Okay, it's the conductivity. Okay, so conductivity depends on the material of the conductor, right? So N is a variable which depends on the material, right? N depends on the material. E and M are basically electrons properties. Tau depends on the material and temperature, right? Material and temperature. So you can say the conductivity will depend on the material of the conductor and the temperature. Okay. So for any given material, at a given temperature, sigma can be treated as a constant. So if you keep the material the same and the temperature the same, then sigma can be treated as a constant. So a higher value of the conductivity means it is a better conductor of current. Okay. Then the inverse 1 by sigma, these are all 10th formulas itself. 1 by sigma is called the resistivity, rho, right? This is defined as the resistivity, rho. So it will be m by ne square tau. Just flip the previous formula. So this will be m by ne square tau. Okay, so they can ask about the fact that does rho depend on temperature, right? So the answer is yes, because tau depends on temperature, right? Tau depends on temperature, so rho must also depend on temperature. So we'll discuss that in a bit. So that is that. And yeah, about the units also just keep it in mind, guys. Rho's unit, as you remember from resistance, its unit is ohm meter, right? Its unit is ohm meter. So sigma's unit will be ohm inverse meter inverse, right? Just take the reciprocal of ohm meter. Now this ohm inverse is also known as Siemens. Okay, so this is actually termed as Siemens. So sigma's unit, conductivity's unit, you can also say it is Siemens per meter. Okay, it is Siemens per meter. And yeah, that's all. That's about resistivity. A question that can easily be asked is the temperature dependence. Okay, about conductivity and resistivity. There is also another formula called as mobility, which is related to this drift speed formula. That is also worth remembering. So mobility, also I can write it here. Mobility. So mobility is basically we use a symbol mu for that. Okay, and it is defined as drift speed divided by electric field. The magnitude of drift speed and electric field. Okay, so from the original relation, it will become E tau by m. E tau divided by m. So this is to kind of get an idea of how mobile the charges are, right? Mobility means how freely are they able to drift inside the conductor. So here, if we are talking about the electron, when we apply an electric field, it starts drifting, right? So mobility of the electron means how easily are they able to drift. So that mobility will depend on the charge of the particle, the mass of the particle, and the relaxation time. Okay, this is what it will depend on. And like for example, if you choose a lighter mass particle, right, instead of the electron, if you choose a lighter mass as your free charge, so if you decrease the denominator, mu will increase, right? Lighter mass means mu will increase. And that is kind of common sense also, right? If you choose a lighter mass, it will drift much more easily when you apply an electric field. So mu depends on these three factors. This formula also you should keep in mind. So this is also important. Okay. And another important thing is mu also depends on temperature, right? Because tau depends on temperature. Tau depends on temperature. So mu also depends on temperature. So now we'll also see how tau depends on temperature. Okay. So what was tau again? Tau was the average time it took for the electron to collide twice, right? So if you increase the temperature, what do you think will happen? When we increase the temperature, frequency of collisions will also go up, right? This is just common sense, because if you increase the temperature, the electron will move much faster, right? So if the electron speed goes up, if these are the copper ions, if the electron was initially moving like this, let's say, then of course the collision will take a lot of time. But if you increase the temperature, then the electron will move much faster, right? So it will collide much faster that way. So if you increase the temperature, how frequently it collides will go up. How frequently the electrons collide will go up, which means the relaxation time will go down, right? Time to collide goes down, right? Collisions happen much quicker. So relaxation time will go down. So temperature and relaxation time have an inverse relation, right? Temperature and relaxation time have an inverse relation. So this is something to keep in mind. So here T is temperature. Temperature of the conductor. Okay. So we covered how tau depends on this as well. So they can ask questions like this. So when you increase the temperature of this conductor, what happens to the mobility of the electrons? Okay. So then the answer is, if you increase the temperature, then tau decreases, right? And if tau decreases, the mobility will decrease, right? So that is how you should analyze that. Similarly, you can get a question on this formula also. Wherever there is tau in the formula, there is a temperature dependence on that quantity. Okay. There will be a temperature dependence in that quantity. All right. So we discussed J equal to sigma E. This is the first important formula, microscopic Ohm's law. Then now we will derive the good old V equal to IR. Okay. So V equal to IR. So in the V equal to IR from class 10th, what was V? V was the potential difference across the conductor, or basically the potential difference across the battery, right? So why are we applying a battery here? The purpose is, we discussed that in order for the electrons to drift, we need to apply an electric field. We need to apply an electric field. When you apply an electric field, the electrons will start drifting to the left, and we will get a current to the right. Okay. Now, in order to set up an electric field, we connect the conductor across a battery. So what the battery will do is, it will maintain a constant potential difference across the two ends of the conductor, and that potential difference is V. This potential difference will set up an electric field inside. So battery maintains a potential difference across the conductor. Okay. And this potential difference sets up a field inside. It sets up a field, electric field inside the conductor. Okay. Okay. And when we have an electric field, we get a current. The same drift velocity idea. So now let's continue. So here we will use the formula from the previous chapter, potential. So the left end of the conductor is at potential V and the right end of the conductor is at potential 0. So the potential difference is V minus 0. So I'm assuming the electric field in this direction is E. Okay, and let's say the length of the conductor is L. So what was the relation between potential difference and electric field? Potential difference magnitude, we can write it as integration of E dot dl, right? But here the electric field is constant, so in integration of E dot dl, I can write it as E into L. So it will be simply E into L. Because electric field is constant, I can use this formula. So what this means is the electric field, I can get it as V divided by L. So electric field, I can get it in terms of the potential difference. Okay. And once I have the electric field, it's easy to find the current using the previous relations, right? We know J, which is current per unit area, equal to sigma into electric field, which is V by L. Okay. Now I want to express it as V equal to IR types. So V, I can write it as 1 by sigma, I can write it as rho L by A into the current. And this rho L by A, I can write it as the resistance. Okay, this is called the resistance of this cylinder, cylindrical conductor. And the relation, we get our Ohm's law expression, V equal to IR. Okay, so the extra thing here was we determined the electric field inside the conductor in terms of the potential difference, right? After that, we were able to derive V equal to IR. Okay. So here the thing is, R is a quantity. So when we have a uniform cylinder meaning the length of the cylinder, I mean the area of the cylinder is constant, okay, and the rho is also constant everywhere. The resistivity of this material also is a constant everywhere. Then what is the resistance of this cylinder? It is given by the relation rho L by A. This is a very important one. Okay, and resistance unit will be ohm, right? Okay, so that is all about this formula V equal to IR. And resistance of the conductor is basically used to control the current through the circuit. So what you will have to do is, we know how to increase resistance, right? To increase resistance is equal to rho L by A. So you can increase the length of the conductor, or you can decrease the area, or you can choose a different material. So if you increase the resistance of the conductor, you decrease the current in the circuit, right? So resistance is used to control current basically. Resistance mainly, its main purpose is to control current in our circuit, okay? So if you modify resistance in the circuit, we can play with the current pretty easily. Okay, so that's all for this. Now a question for you guys. What is the resistance in case A? Okay, and what is the resistance in case B. So give this a try, guys. Give this a try. I think I have a timer here. Take 2 minutes. What is the resistance of this cuboid in the first case and the second case? Anyone with the answer? Okay, so how do we solve this? So what is the main difference between the first diagram and the second diagram? It's how the wires are connected, right? How the wires are connected. So in the first case, the wire is connected between this rectangular edge and this rectangular edge. So if you connect the wire like that, so I'm drawing the side view of figure A. So wire is connected like this and like this. This is your length L. If you connect the wire like this, the potential difference is set up like this. Okay. So here the electric field or the current will be along the direction of the length. Okay. The current will be along the direction of the length. In the second case, the difference is the current will be not along L but along H. In this case, the current will be along the H direction. So that is the main difference between case 1 and case 2. So now you can just use that formula, okay? The same cylinder formula, you can use it here also. So the resistance here will be rho into, so L is basically parallel to the length, parallel to the direction of current, okay? So that will be L here divided by area of cross section. So in the area, what area do we choose? We choose the area perpendicular to the current. Okay, whatever that area perpendicular to the current is, we choose that. So in this diagram, it's going to look like this. We choose this area. What is the area of this rectangle? H into B. So rho L divided by H into B. This will be the resistance in case A. And in case B also, you can similarly get the answer. The resistance in case B, you can similarly get the answer. So in case B, the only difference is now current is parallel to H, right? Current is parallel to this side length H. So instead of L, you will substitute H. And what is the area, perpendicular area to the current? That is going to be this rectangular area, this top rectangular area. That is actually, this length is B and this length is L, right? So L into B. So rho H divided by L into B, that will be the resistance in case B. Okay. So that is the resistance in case A and case B. So depending on how you connect the battery to the conductor, the resistance will be different. Great. Then, so temperature dependence on resistivity. So we briefly talked about this earlier. So when we increase the temperature, resistivity depends on the temperature, right? So relation of resistivity with that rho was m divided by n e square tau. So when temperature was increased, when we increased the temperature, we discussed tau goes down, right? So if tau goes down, rho goes up. So resistivity goes up. So you can kind of say there is a proportional relationship between resistivity and temperature. So if you increase the temperature, you also increase the resistivity of the conducting material, right? So the exact relation is something like this: rho naught 1 plus alpha delta T, okay? And here rho naught is the resistivity at a T naught temperature, at reference temperature. Rho naught, so I'm going to write it like this: alpha into T minus T naught. So rho naught is the resistivity of the conductor. It's the resistivity at T naught temperature, okay? And rho is the resistivity at T, okay? So if you increase the temperature of the conductor by, increase it to T, then this is the new resistivity that you obtain, okay? So this is a relation that gives us the resistivity. This you can slightly modify it and write it this way also: rho naught 1 plus alpha delta T, okay? Now here alpha is known as the temperature coefficient of resistivity. Okay, this depends on the material, okay? This will depend on material to material. Okay. Now what else? Now here, what kind of questions can you expect? They will, give you the resistivity value at some reference temperature. They will also give you the alpha value, and then they will ask you the resistivity at a new temperature. So you can use this relation and substitute and get the answer. Okay. So this relation is also important. So like a simple example can be, they will give you at 0 degrees Celsius, the resistivity was, let's say 10 raised to minus 5 ohm meter, and they're asking the resistivity at 30 degrees Celsius, okay? And the alpha value will also be given. Alpha is, let's say, 10 raised to minus 4. Now 3 into 10 raised to minus 6. So alpha's dimension is 1 by temperature. Okay, so something like this. So and then you can just substitute. Rho naught and T naught is known, T is known and alpha is known. So you can substitute and get the answer. Okay. Then what else is there? So then there is some theory, okay, regarding resistivity values and how we classify that material. So you guys must have covered this. So different types of materials, we classify these materials according to their how good of a conductor they are, right? Or basically on the basis of their conductivity. So if they're very high in conductivity, which means very low in resistivity, then they are classified as very good conductors. Okay, very good conductors. So these are materials with high conductivity and low resistivity. A typical conductor of copper has this as the resistivity. So as you can see, it's 10 power minus 8. It's a very low value for resistivity. That's why it's an excellent conductor, right? So resistivity increases with the rise in temperature. This we discussed. And insulators are basically those type of materials which don't allow a current to flow through them. Okay. So like if you take an insulating material, you can apply an electric field inside it, but that will not cause any flow of charges inside. The current inside will still be zero. Okay. You can also treat this material like having infinite resistance, right? So typical value may be 5 into, as you can see, 10 raised to 17 ohm meter. So very, very high value of resistivity, practically infinite, right? So it won't allow any flow of current through it. Okay. So I have written some examples also here. You will get the PDF after the lecture, so you can read them. You should also read the NCRT for these points as well. Okay. Then semiconductors, we will discuss it later. So this has a different mechanism of conducting electricity. Okay. It's not exactly like the conductor which we discussed before. Here we will talk about the logic of diodes later in semiconductor chapter. But their conductivity is somewhere in between. Okay. They're not as good as conductors, but they are decently good. Yeah, so that is all for the conducting material categories, right? There's also superconductor, but we can talk about that later. And okay, so now we can talk about the series and parallel formula. Okay, so the combination of resistance, the class 10th formula. Great. So series formula, you guys all know this from class 10th. If you want to replace it with an equivalent resistance, the R equivalent will be R1 plus R2 plus R3, right? So it's easier to derive it after covering KVL and KCL, right? But we can also do it without them, right? Today we won't be able to reach KVL. So how do we do this? First of all, what does it mean by an equivalent resistance? So in the example, we had 3 such resistors connected to a battery, right? An equivalent resistance means we want to replace the set of 3 resistors with a single resistor, okay, with a single resistor, such that the current drawn from the battery is the same. So if the battery's voltage is V, we want the current drawn from the battery to be same in both cases. Okay, so current in that case, if it is I, current in this case should also be I. So that is the definition of the equivalent resistance. Okay. So R1, R2, R3 we want to replace with a single resistor. Okay, so the first thing is about series combinations. Okay, everywhere in this conducting wire that you are seeing, including the resistances as well, the current is going to be the same. So the current here will also be same, I. Current in R2 will also be I, and current in R3 will also be I. So in the equivalent diagram also, current will be I. Now here it is easy to write V equal to IR. Potential difference across the resistance is V. And what was Ohm's law? V equal to I into resistance. Right? Whenever you have a resistor, right, and you know the potential difference across the resistor, V, and let's say the current through it is I, then you can always write V as IR, right? V as IR. So here the issue is the potential difference across R1 will be something else. So let's call it V1. Across R2 it will be something else. Let's call it V2. And across R3 it will be something else. Let's call it V3. But individually we can write what is V1, what is V2, what is V3. Because we can apply Ohm's law in this R1 resistor. Then we will get V1 equal to IR1. Similarly, apply Ohm's law in R2. So V2 equal to IR2 and V3 equal to IR3. Okay. So apply Ohm's law in the three resistors one by one. Then the next fact is, if you add up these voltages, V1 plus V2 plus V3, that will be equal to V, which is the total potential difference applied by the battery. So V will be equal to V1 plus V2 plus V3 in this case. Now V1, V2 and V3 use these relations, and instead of V we will use this relation. Okay, so instead of V we will write it as I into R equivalent. Instead of V1 we will write IR1. Instead of V2 we will write IR2. V3 will be IR3. And in case there were more resistors in series, it will simply be plus IR4 plus IR by IR5 and so on. So in all these terms, the current term cancels and we get the R equivalent as the sum of the resistors. However many resistances are there. So this you can also write it as sigma Ri. Right? Just add up all the resistors and you will get the equivalent resistance. Okay. All right. So great. Now, if you also if you have the R equivalent, you can also find the current through the circuit. The current will be V divided by R equivalent, right? So in this question, the current will be V divided by R1 plus R2 plus R3. So that is the use of finding R equivalent. We can instantly find the current through the battery, right? If you find the R equivalent, it will be simply V by R equivalent. Okay, so now one parallel formula is also left. So parallel logic also is the same. It's a similar logic. In parallel, the main logic is the battery is basically connected to this point A and to this point B, right? So the potential difference between A and B, the battery will maintain it as V only. Potential difference between A and B, the battery will maintain it V constant. Okay. Now R1 resistance has a potential difference of V. R2 resistance also has a potential difference of V because they are in parallel. Okay, or basically because they are connected between the same points A and B. So their potential differences are same in parallel combination. But the currents will of course be different, right? So if the battery is giving out a current I, this current I will split here. So some fraction I1 will go here and some part I2 will go here of the total current I. Current will be different, but the potential differences are the same. So then what can we say? So once again, we want to replace it with one R equivalent, with one single R equivalent. And we want the current to be the same in both cases, right? That is what we mean by the equivalent resistance. So here we can apply that equation V equal to I into R equivalent. And here what can we do? We can apply V Ohm's law for R1 and R2 separately. So that will give us V equal to I1 R1, right? And V equal to I2 R2. Okay. Now we also know that this incoming current I is split into I1 and I2. So this I can also write it as the sum of I1 and I2, right? So now just substitute everything. I write it as V divided by R equivalent. I1 will be V1 by R1. Sorry, V by R1. And I2 will be V by R2. So in the parallel game, the potential difference cancels out and we get 1 by R equivalent as 1 by R1 plus 1 by R2, and in case there were more resistors, it will simply add up. So 1 by R3 and so on until 1 by R. Okay. So for the parallel formula, the R equivalent, you can write it as sigma of 1 by Ri. So add up the 1 by Ri's. Okay, from I equal to 1 to n. Now the formula for two resistors, you should just directly remember it. Okay, so if you take the LCM, R equivalent, you will get it as R1 R2 divided by R1 plus R2. This is the R equivalent. And once again, if you have R equivalent, you can directly get the current. You can directly get the current leaving the battery. So current leaving the battery will be V divided by R1 R2 divided by R1 plus R2. V divided by R equivalent. Okay. Okay guys, so I guess the time is up. Okay, so there are more things we had to discuss. So in current electricity, we'll have an additional lecture. Don't worry, we will, in that lecture, we will cover KCL, KVL, Wheatstone. What else is there? The measuring devices, right? Galvanometer, ammeter, those things. Okay, so there are a lot of things left. We will cover that in the next lecture, okay? So today's lecture is ending here. So that's all guys. That is all. Okay. Goodbye guys, take care and good night. Okay.